Let's look at a couple of examples of these matrix operations in application. We're going to go back to that table that we were given at the beginning and specifically look at scenario 3 that I wrote out and see how we might get exactly what we're looking for in that scenario. Let's dive in. Write the matrix operation that would be required to complete scenario 3 above, then perform that operation, interpret the results. Let's go back up. Scenario 3 says, what if you wanted to see the numbers for 6 ounces of chicken, 2 cups of broccoli, and 3 ounces of cheese? So when we say numbers, we're talking about total calories, protein, and total fat. Okay, totals for each of these if you had a meal with 6 ounces of chicken, 2 cups of broccoli, and 3 ounces of cheese. Well, to get the total number of calories, really we would want to be able to multiply this by 6, this by 2, and this by 3, right? And the same thing here to find the total protein. That by 6, that by 2, and that by 3. This by 6, this by 2, and this by 3. So in essence, what I want is to multiply each of these columns in this matrix by 6, 2, 3. Keeping in mind the fact that I multiply rows by columns, I am going to want to put a row out here that is 6, 2, 3, so that I would multiply the 6 by the 30, the 2 by the 31, and the 3 by the 115. Then I'd multiply the 6 by the 6.5, 2 by 2.5, 3 by 6.5, and so on. That operation, that matrix operation, will give me the total number of calories for that meal of 6 ounces of chicken, 2 cups of broccoli, and 3 ounces of cheese. Let's go write that down here in the space. Six, 2, 3, and then we want to multiply that by, what was it, 30, 31, and I think 115 going down. I may have to write these numbers down. 6.5, 2.5, 6.5. I know normally we read across, but these numbers are easier for me to think about in terms of those counts. And last is, I think it was 1.39.4. 1.39.4. 0.3 and 9.4. Okay. When we multiply these, keeping in mind our process, first of all, this is 1 by 3 and this is 3 by 3, so our result will be 1 by 3. We want to multiply this row by this column. 6 by 30 plus 2 times 31 going across the row and down the column, plus 3 times 115. Then we do that same row by this column. First row, second column is going to come over here. 6 times 6.5 plus 2 times 2.5 plus 3 times 6.5. And then last is going to be that same row by this column. I'm going to have to come down here, but know that it should be in this space. I'm just out of room. 6 times 1 plus 2 times 0.3 plus 3 times 9.4. Let's come down and figure out what these numbers are. 180 plus 62 plus 345 is 587. Then the next one, 6 times 6.5 plus 2 times 2.5 plus 3 times 6.5 gives me 63.5. And the last one there in green, 6 plus 0.6 plus 3 times 9.4, 34.8. Now let's interpret this. That's what we really care about, right, is the interpretation. The 587 would be the total calories for the meal. Because remember, what we did here is we said we had 6 ounces of chicken, multiply that by the 30 calories per ounce. 2 cups of broccoli times the 31 calories per cup of broccoli. 3 ounces of cheese times the 115 calories per ounce. This 63.5 would be the total grams of protein for the same reason. And the 34.8 is the total grams of fat for the whole meal. That's our interpretation. Let's do one more example problem. Suppose a furniture company has 2 stores, each selling the same kind of dresser, nightstand, and bookcase. You know what? We've already seen an application of this. I'm going to go ahead and skip this. You are welcome to work on this and calculate it and try to interpret that. But just for the purposes of time, I don't need to beat a dead horse in that application area. So I'm going to skip that one. Let's go down to this matrix equation idea. We already talked about this concept, so I'm kind of skipping over that too. Matrix equations. We can write a system of equations, so now going back to that idea of systems of equations, as AX equals B, where A is what we call the coefficient matrix. X is the variable matrix. It will contain all the variables. And B is the constant matrix. Here's how it works. We take just the coefficients. So this is different than the augmented matrix. Make sure you keep these separate in your brain. The matrix equation will take just the coefficients. 3, 2, 1 for the first equation. 1, negative 1, 3. 4, 0, negative 2. This is what we call the coefficient matrix. Now, if we multiply that by a variable matrix that contains the variables vertically, what we know is that if we were to multiply those, we would multiply the 3 times the x plus 2 times the y plus 1 times the z, right? You multiply the row by the column. So you get 3x plus 2y plus z. Notice that is exactly what we have here. We're going to say that has to equal 4. We notice if you multiply the next row by that column, you get x minus y plus 3z. That is exactly what you have here. That has to equal 6. And then the last one has to equal negative 1. what we have written above, this is my A, the coefficient matrix, times, this is X, the variable matrix, contains all the variables, and this is B, the constant matrix. In the next section, we are going to talk about why we need this, or why is this helpful. What would we like to be able to do? Obviously, we'd like to be able to solve this system of equations, but how do we do it is what we're going to discuss in the next section.